This is John Black, super chemist, and the best would be a 1-to-1 ratio. Okay, now if you remember, if I was making the uh, benzyl chloride, right, with one chloride, we ended up with 50% toluene left there and 50% or 45% or something like that of the because we only chlorinated enough, to chlorinate that much. We don't want to do any more than that because we'd have a lot of impurities, right? So when you get done making this, if you wanted to hydrolyze it, you could just leave the toluene in there. You want to put it in there anyway. If it wasn't there, you'd put it there because you want a 1-to-1 ratio is best, right? So if you get done with your reaction and 46% is this and 56% is toluene, hey, that's good enough, man. They just leave it in there and go to hydrolysis. You don't even have to get the benzyl chloride out of it. You don't have to get the toluene out because it needs to be in there. After hydrolysis, benzyl alcohol, let's say you're just making benzyl alcohol, and even if you're making benzaldehyde, there's a lot of benzyl alcohol you're going to make because of that's the contamination. When you try to make this, you're always going to end up with a large portion of this. So you're going to make some benzyl alcohol either way. Benzyl alcohol has almost the same density as the spent hydrolyzing agent solution. So it's going to trying to phase separate it is difficult. So you're going to lose 3 to 5% loss by weight because trying to get that out is going to be hard, okay, because they have the same density. Water is soluble in benzyl alcohol, so 4.9% will be water. When you get your benzyl alcohol finally out, 4.9% of it's going to be water, you know what I'm saying? Because that's how much is soluble in it. Now 3.9% by weight is benzyl alcohol solubility in water. It's the opposite way, right? And the way you can lower that is by adding sodium chloride. Just like anytime you want to get a hydrocarbon type molecule out of water, you add sodium chloride. That's the go-to thing to do. And then that way you can get the solubility down to only 1%. Instead of losing 3.9%, you lose 1%. That's a lot better. This is just a generic formula and generic instructions here. But I got them on the internet, so I thought I'd put it down. Here's the formula. They use calcium carbonate as their hydrolyzing agent. 500 milliliters of water, 90 grams of this, 150 grams of that. Add it reflux for 4 hours at 130 C, and then steam distill till no more oil comes over, meaning the oil of the benzaldehyde you made from this. Your final distillation of benzaldehyde should always be done under a vacuum because it's very easily oxidized to benzoic acid. And if you don't take the oxygen or the air out, as you distill it, it's just going to turn from a nice, clear, beautiful, clear liquid into, a tinted brown, tinted color that you don't want. The other thing is you can purify benzaldehyde with bisulfite adduct. Okay, just I'm not going to go in depth about it. If you have questions, you can always ask, or wait till I do a video on this winter. But basically, just add the sodium bisulfite to the benzaldehyde, and you stir it up. You have to have a lot of bisulfite in there extra. You know what I mean? Have the water saturated, stirred a lot, and this will form a solid adduct with this. And then you can filter the solid out and wash it. And then when you turn it back into benzaldehyde, you can just use any kind of base like sodium carbonate, and Again, you want it to be saturated with sodium bicarbonate. You want it to be in excess, and mix it with the benzaldehyde bisulfite adduct, and it will turn it back into benzaldehyde. Now you might say, well, so it's still got a bunch of crap in it. Well, not really. It only has water, benzaldehyde, and everything else is a solid. Now you can easily either throw some DCM in there or some ether and soak up the benzaldehyde and get it out of the water, and then separate it in a set funnel, and then take the DCM benzaldehyde and just evaporate the DCM off because it has such a low boiling point compared to the benzaldehyde. Or you can just distill off the water and then distill the benzaldehyde. Either way, you're going to have to distill the benzaldehyde. I do it under a vacuum. And then just try it with molecular sieves, you know what I mean? Here's the equation for the benzaldehyde bisulfite. Get the bisulfite adduct. As you can see, it's a back and forth reaction. If you have this, you want to go here, you use bisulfite. If you want it to go back, then you use bicarbonate. Now, last winter I made adduct with acetone. I did it with sodium bisulfite and just sodium sulfite, and it both times produced a solid. I never took it back to acetone though. But I think when you do that reaction, you release SO2 from this right here. So you'd have to do it in a fume hood or whatever. But I'm unsure because I've never actually done it. Now, I went over the video, all the videos I put out, and I'd see if I did any mistakes or any whatevers. And one of the things I saw that I made a mistake, this was the apparatus. This is where your UV comes in, you're refluxing your toluene. And this is just a drying agent. And this is where you make your chlorine. It comes in to the drying agent, and then it comes into here. When I said you should have your UV at the end of the tube, I was pointing here, even though I should have been pointing here. You want it where the chlorine is, the whole plot here where the chlorine is coming out of the tube. The rest of this that you see is in green. That should all be covered with foil, tin foil, because you don't want the UV reacting, making free radicals over here when there's no toluene to react with. The toluene and chlorine should be anhydrous when chlorinating. I only mentioned that the chlorine should be. You should also have your toluene. I mean, you don't have to throw sodium in to, make sure that it's totally whatever. But, put some molecular sieves in there and dry it up. So once you look at the mechanism, there's chlorine, there's UV. UV breaks the homolytic cleavage, breaks that bond there. You have a chlorine radical. It attacks over here and plucks off this hydrogen, so it have HCl. And now you got a free radical here on the toluene. So the toluene jumps over here and grabs the chlorine. And now you have benzyl chloride. But you also have another free radical chlorine, which will repeat the process. It'll grab a hydrogen off of the another toluene molecule and continue this cycle. But think about it. Let's say you have two, you're not just making one chlorine radical at a time, you know what I mean? You're making a bunch of them at a time. So that means you're going to make a bunch of these at the same time, right? Two of these toluene radicals could actually link up together, right? And form this. And then this can go into the process. A chlorine radical or one of these radicals can come and pluck off a benzyl hydrogen off of there or a benzyl hydrogen off of there and make that into a free radical, and so on and so forth. One last thing I wanted to mention was the silver nitrate. When I was talking about when you're hydrolyzing this stuff, you want to see if you have any chloro groups left. You can take it and put it in some silver nitrate that's in some alcohol. If there's a precip, then there's still chloro groups. I'm not sure if that is just for this or it's for this. I would hope it would be for this, but I'm unsure what type of chloro groups. Do they mean a benzyl chloro group or a benzene chloro group? I don't know. I'm unsure. The other thing was is the blue light. I am definitely sure that it needs to be between 21 and 494 nanometers wavelength. That's blue and green light and probably some violets in there. Would you go for green? No, I would go for blue because blue is definitely enough to do it and extra, you know what I mean? But it's not enough to break any benzyl chlorine bonds, you know, these carbon chlorine bonds here that you're making. So all my facts, you know, I got from the internet, you know what I mean? So take them as take them as you see them or whatever. I think that I got all the quirks out of these videos, and I think other than a silver nitrate test to see if you're done hydrolyzing all the chlorine groups off, other than that, I don't see anything wrong with any of the videos. Saying that 400 nanometers is too strong, you know, that's the weakest UV light you can use, so that means all the stronger UV light is not good either. You know, that you will be, and see, not only will you be having this UV light coming from the sun if you use the sun that makes it through the glass and the ozone, you'll also have between 400 and 421 nanometers that's violet visible light that will also be breaking these benzyl carbon chloro bonds. So keep that in mind. I am definitely sure about this blue thing, and the next video I do is going to be about how to buy blue lights that give you, I think it's like 450 to 475 or 480 nanometers, and that's exactly what you want. You want it in the blue range as much as you can, you know what I mean, as high as you can go, but under 421 nanometers. So, and you can probably buy the light for, you know, 30 bucks or something. Uh, and I will talk about how to figure out the wattage. Remember I was talking about intensity. If you have a little battery operated keychain thing that puts off blue light, don't expect that to work. It'll work, but you don't have enough photons to do the reaction in a quick, orderly fashion. You know what I mean? You're going to be there for days trying, because you're only putting out 10 photons out of your thing every hour. You know what I mean? I'm exaggerating, obviously. But I will go into how you buy the lights, how you size it so that you know that you're getting enough wattage, and all that kind of stuff there. And then I will prove it, because I will do this experiment here, like I said, with the DCM, and I will, because I can get DCM by the truckloads at any hardware store. And I will chlorinate it all the way to the fullest. So that's the easiest type of halogenation or chlorination, is when you're doing it to saturate it, because it's going to want to saturate it. And if that's what you're going for, then that's great. If not, then it's not so great. But I can say without a doubt that you know, the nanometers that I'm saying, I can say without a doubt. I mean, for this kind, not for this, but for this kind of chlorination, is definitely 400 nanometers is not right. It's not wrong. I mean, you're still going to get the reaction done. It's just not going to be as good. You know what I mean? You want to be, like I said, from 421 to 494 nanometers. And you want to be closer to the 421 than you do to the 494, because that'll put you closer to the ultraviolet, or closer to being more powerful. So I wanted to apologize for, you know, putting these videos up and down and up and down. But I swear they're all good now, and everything I'm saying is good information. Seems I'll have a great day, and always remember, science is great. Anyway, since I'll have a great day, and always remember, science is great.